Right, now it's time to practice with the weak acid, strong base titration. So these get a little bit trickier because there's a lot more that goes on with that equilibrium setup that we have. So if we've got 30 milliliters of 0.5 molar acetic acid this time, along with 0.5 molar sodium hydroxide. So we're going to look at how much sodium hydroxide has to be added to reach half the equivalence point. In other words, to get halfway to the point where H plus equals OH minus. Then we're going to find the pH at that point. And then we're going to identify the main species that are present in the solution after it's been titrated to the half equivalence point. The first thing we need to do is find out how many moles there was in our sample initially, so in our acetic acid. Okay, and so you'll notice here that I didn't write 0.5 molar concentration of H+. I wrote 0.5 molar acetic acid because this is a weak acid, which means it does not have 100% dissociation, which means what we are looking at here is the acetic acid as a whole. And so in the original sample, we would have 0.015 moles of acetic acid. So what volume of sodium hydroxide has to be added in order to reach halfway to the equivalence point? So at the equivalence point, the concentration of H plus is equal to the concentration of OH minus. So for a weak acid, weak base, at the equivalence point, the concentration of acetic acid, CH3COOH, would have to be equal to the concentration of OH minus. So then at the equivalence point with this system right here, the concentration of hydroxide would have to be equal to that. So we'd have to add 0.015 moles of sodium hydroxide to get to the equivalence point. If we're talking about halfway to the equivalence point, that means we need to add half of the moles, which means we need to add 0.0075 moles of sodium hydroxide. In order to get that number of moles, looks like we'd have to add 15 milliliters of the sodium hydroxide solution. So at that point, we would be halfway to having these two concentrations equal. And sorry, in part B, it looks like we're finding the pKa, not the pH, like I said earlier in the video. So we started off with 0.015 moles of acetic acid, CH3COOH, and then we added some hydroxides to it. And what that strong base is going to do is it's going to rip those protons away from the acetic acid that normally wouldn't give them up on its own. And it's going to leave us with some acetate and some water. So if we have taken our acetic acid and turned half of it into products, so we react half with it and get halfway to the equivalence point, that means at this point, halfway to the equivalence point, we are going to have half acetic acid and half acetate. So that means that the concentration of CH3COOH is equal to the concentration of CH3COO minus. So those two concentrations at this point are equal. And that's when we're halfway to the equivalence point. So when we do weak acid, strong base titrations, Henderson-Hasselbalch equation more often than not is going to pop up. And so here's an example of how we could use that to find the pKa. And so we know that pH is equal to pKa plus the log of the concentration of the salt divided by the concentration of the original acid. And so at this point, halfway to the equivalence point, we know that those two values are equal, which means our ratio right here is 1. So the log of 1, if you don't believe me, type in your calculator, but the log of 1 is 0. And so that means the pH is going to equal the pKa plus 0, which means the pH equals the pKa. And so at this point, the pKa is going to be 4.74. So then the main species that would be present at this time would of course still be the acetic acid, and we've got an equal concentration then of the acetates, and because of the sodium hydroxide that we've added, it's going to leave behind some sodiums, so the cation that are floating around. Since those are unhindered, they don't bond or anything, they're going to go off on their own, and it's still going to be an acetic system because we are below the equivalence point, and so that means there's also going to be H3O pluses or H pluses present in some concentration. So here's a picture of the titration curve for the pH versus volume added of sodium hydroxide with a weak acid strong base titration. And you notice this one looks a lot different than the strong acid strong base. So once again, we can recognize a weak acid strong base titration by its curve. And so in this case, we are starting with a pH that is slightly higher, and that's because it's a weak acid, so it doesn't have as many H pluses as a strong acid would. And then the increase right here is a little bit curved and a little bit steady, so it's almost exponential as it goes up. And so right here, this would be the values we just looked at, where the pKa equals the pH, so that's halfway to the equivalence point. And then once we get to the end point, or the equivalence point, we see that it's right here. It's not quite as steep of a jump as it was with a strong acid, strong base, and then we get that steady climb again. One thing we notice right here, the equivalence point, once more, is right halfway the intersection between those two jumps, but in this case it falls with a pH that is greater than 7. So the reason that pH is above 7 is because at the equivalence point, so at this point right here, the concentration of acetic acid was equal to the amount of sodium hydroxide we added. And so when those two combine, we already saw it produces water and the acetate ions. And we know that acetate ions, which would be the conjugate base of a weak acid, is therefore a strong base. And so this ion, which is going to be highly present there at the equivalence point, is going to adjust the pH, and that's because it's going to react with water that is inside of the solution, obviously, to produce OH minuses and CH3COOH, and so that's going to therefore raise the pH. And also this little region right here, you see how it's kind of curved a little bit, so it's not a straight line like it was before. That's because during this range right here, we're actually creating a buffer, because we've got a weak acid, so the CH3COOH, the acetic acid, and then we've produced some of its acetate. As we are adding that sodium hydroxide, we are creating a system where there's a weak acid and its conjugate base, which we know sets up a buffer system, and so that causes the pH to change very, very slowly. And so at first it increases a little bit, but then the rate of change decreases as the buffer solution is created. But eventually that buffer maxes out and we jump up. And here's some more information. So a weak acid, strong base titration, we looked at that. We're not going to look at a weak base, strong acid titration because it's essentially the exact same thing, only backwards. We're dealing with a weak base and a strong acid. And so we would get a similar curve, but we would have kind of that slow increase right there, then a drop down, and then we would wind up with a slightly acidic at equivalence point pH. But as far as process, it's the same. We'd get a slight buffer right there, our smaller jump, and then that steady increase right there, a pH less than 7 because we have a weak base, which is going to have a conjugate acid that is a stronger acid. One last titration curve to show you real quick so that you recognize them would be one for a polyprotic acid. And so polyprotic acid, one that has more than one proton. And so what we see then is we see two different equivalence points. And so we've got that steady increase and then a spike, and then a steady increase and then another spike. So this would be the point where we are at 100% HA. So if we started with H2A, this is when we've removed all of the first protons and we're left with just HA. And then as we add more and more sodium hydroxide, more base to this, once again it steadily increases, and then eventually we're left with just A2 minus. And so this would be the point where we've ripped off all of the secondary protons. And so at halfway to the equivalence point on both of these is the point where the pH is equal to the pKa. So we can determine the pKa of a weak acid, weak base, or a polyprotic acid because it's going to be the point when we're halfway to the equivalence point what the pH is, and the pH would equal the pKa. So like at this point right here, that's halfway to this equivalence point, and we see that the pH is about 3.24, and so that means the pKa for this particular dissociation would be 3.24 as well.